Good evening, everyone. Can you hear me? Can somebody please confirm? Yeah, okay, thank you. Uh, Welcome back to our GATE ECE previous year questions solutions. I'm Shankar Rao, a PhD scholar from Electrical Engineering from IIT Hyderabad. Today what we will do is like we will solve uh, some 4 to 5 problems from signals and systems, mainly based on the questions were like given in the previous year GATE papers, and also we'll see revise some of the concepts related to that, and we'll solve those problems. If time permits, we may solve some problems on digital electronics. Okay, so today we'll solve a problem from Fourier transform and sampling and continuous Fourier series. So first problem will solve from Fourier transform. So this is the question. This was given in GATE 2017 ECE set 1 for 2 marks. So a continuous time signal x of t equal to 4 cos 200 pi t plus 8 cos 400 pi t, where t is in seconds. The input to a linear time invariant filter with impulse response. The impulse response is given. Let y of t be the output of this filter. The maximum value of y of t is. So this is the question given. So can somebody please tell me like how we can solve this? You can unmute your mic and feel free to say something. So you have gone through the Fourier transforms, right? Yeah, can somebody can speak out? You have gone through Fourier transforms, right? Fine. So in the problem it is given uh, a continuous time signal x of t is given, is input to a LTI system with impulse response, that is impulse response of an LTI system given h of t, and x of t is input sum of two sinusoid signals that is given as input to this. So let us say y of t is the output of this filter. This, let us say, the filter that is given, output of a filter is y of t. Then what is the maximum value of y of t? So what is the maximum value of y of t? Means maximum magnitude of y of t we need to find out. So you know, for an LTI filter, if x of t is the input and h of t is the system response, then we know the output is x of t convolved with h of t. So here what we will do is, instead of doing that, till two ways we can do. One is we can find out the Fourier transform. Sorry, instead of doing this, we can solve this problem in Fourier domain. In Fourier domain, for this frequency domain, we can solve. So we will find out h of omega, x of omega, and we can multiply them. So in Fourier domain we can solve this, or else we can find the Fourier transform of h of t and we can solve it. Let us solve this. X of t is 4. Yeah, x of t is 4 cos 200 pi t uh, plus 8 cos 400 pi t, and h of t is given 2 sin 300 pi t by pi t, 2 sin 300 pi t by pi t when t not equal to 0, and it is 600 when t equal to 0, right? Yeah, and it's 600 when t equal to 0. Now what we will do, since we know the output is y of t is x of t convolved with h of t. So if you apply Fourier transform, then we know output to Fourier transform, let us say y of omega, convolution will become multiplication in the frequency domain. So x of omega into h of omega. In this way we can find out. So what we will do, we will find out the Fourier transform of x of omega and Fourier transform of h of omega. Both will find out, multiply. Then what we will have is y of omega. If you find out inverse Fourier transform of it, we will get y of t, from which maximum value we can find out. Or else another way is, so let us say we have some filter or some system whose impulse response is h of t and whose Fourier transform is h of omega, and let us say some sine or cosine signal we are giving as input to this, a cos some omega naught t plus some theta, a cos omega naught t some theta if we are giving as input, then output is same, the sinusoid signal only, but the amplitude will be multiplied and a phase will be shifted. So let's say this is an LTI system and h of omega, so let us say its magnitude is h of mod h of omega and its phase is mod h of omega naught. This magnitude, let me say k, this magnitude and mod h of omega, this is the phase. Now the output is same as that. Now the output will be scaled version. So input is a cos omega naught t plus theta. So a into this will be multiplied by the magnitude at omega naught. See, input frequency is omega naught. At that frequency, what is the magnitude? And cos of omega naught t plus theta, and phase is added. That phase is h of omega naught t. Okay, so at omega naught t, the magnitude and phase we need to find out of the filter or the system. The magnitude multiplies the amplitude and phase will be added to the phase of sinusoid. So this is true for sine or cos or exponential, some e power j omega, these kind of signals. Okay, so this kind of problems will often see in GATE papers. So we will see now, in this way we'll solve this problem. Now we have h of t is given when t not equal to 0. H of t is given. Now we will find out the Fourier transform of h of t. So you know, let us say Fourier transform of h of t is h of omega. You know how the Fourier transform is defined. H of omega is integral minus infinity to plus infinity h of t e power minus j omega t dt, which this is h of omega, right? But here in the problem, uh, h of t is given as sinc function, so we know already how to find out the Fourier transform of a sinc function. So this is given as 2 sine 300 pi t 2 sine 300 pi t pi t by pi t when t equal to 0. This is the sinc function, right? We know Fourier transform of sinc function if the signal is sine at by pi t. Last class also we discussed this. Its Fourier transform is a rectangular function in the omega domain. So if it is omega 0, so this is a, right? From minus a to plus a, this rectangular pulse will be, and its magnitude is 1. So this is the Fourier transform of this one. So from this we can find out the Fourier transform of this, right? Fourier transform of this is, so a is 300 pi right here. So a is 300 pi. So minus 300 pi to plus 300 pi omega domain, and amplitude, there is a amplitude 2. This is h of omega when t not equal to 0, and also we have h of t equal to 600 when t equal to 0. That means h of t, how I can represent, actually h of t you can represent as from this 2 sine, h of t actually is 2 sine 300 pi t by pi t plus 600 plus 600, right? This is h of t. Now how to find out the Fourier transform of this 600? It's a constant. Can somebody tell me what is the Fourier transform of 1? What is the Fourier transform of 1? Del of t. Del of t. Fine. Fourier transform of 1 we will see. We know the Fourier transform of del of t is 1, right? Fourier transform of del of t is 1. If you apply duality principle for this, then Fourier transform of 1 is 2 pi del of omega, right? If you apply duality principle, then Fourier transform of 1 is 2 pi del of omega. Similarly, in this case 600, so its Fourier transform is 600 into 2 pi del of omega. So 1200 pi del of omega. This is the Fourier transform of 600. So we have the Fourier transform of this, we have this one, and Fourier transform of 600 is 1200 pi del of omega. Now what is h of omega? The h of omega is sum of those two. This is h of omega. So we have an impulse that is 1200 pi del of omega, that is at 0, right? Del of omega is exists only at 0, right? So this is omega domain, omega, so minus 300 pi to 300 pi. This is h of omega, right? So we have h of omega. Now we found out this is h of omega. Now if the signal is passed through this, what will happen, we'll see now. Now the signal given are 2 cos 200, 4 cos 200 pi t and 8 cos 400 pi t. So x of t is 4 cos 200 pi t plus 8 cos 400 pi t. Now can you tell me, this is a filter, it's what, it's a filter, right? Low pass filter. Now can you tell me which signal will go out of that filter and which signal will be stopped? So x of t we are giving here as input. Here we have h of omega. Then what frequencies will go out?
So 200 cos 200 pi kt will pass out and 400 pi t will be rejected.
Exactly, yes. So since if you see the filter, the first term you take x of t, the first term if you take its frequency omega is 200 pi. Now at 200 pi, what is the gain? Gain of the filter is 2, right? At a 200 pi somewhere here, the gain of the filter is 2, right? So I already told you right here. I have explained. Suppose if a sinusoidal signal is passing through some LTI system, then what magnitude will be multiplied by the gain of the what to say the filter at omega naught at that frequency, and phase will be added, right? That's what I said, right? Now if you see here at 200 pi, what is the magnitude? 200 pi, the magnitude is 2, right? Magnitude of the filter is 2. That means for this 4 into 2 with 2 it is multiplied, and cos of 200 pi t. And what about the phase? There is no phase, right? Here, zero phase. Since it's a rectangular pulse, right? H of omega is a rectangular pulse. So it's a real one. So you will not have any phase, right? Zero phase. That means no phase is added. Similarly, for the second one, 400 pi t, 400 pi is the frequency. Now, what is the cutoff frequency? You can say 300, right? At 400 pi, somewhere here, what is the gain? Gain is 0, right? At 400 pi, if you see, h of omega, gain is 0. That means the second signal is multiplied by 0. Then something cos. That means the second signal will be suppressed because at 400 pi there is no gain. Gain is 0. The first signal will go out of the filter. So what you got is y of t is 8 cos 200 pi t. So in the question it is asked, what is the maximum value of this? We know 8 cos 200 pi t means something like this we will have, right? Something like this. So the maximum value is this one, right? 8. 8 is the maximum value, right? Is that okay? So maximum mod y, if you take mod y, the maximum value of cos is 1. So maximum value is 8 is the maximum value. So 8 is the answer for this. Uh, so is that okay? Uh, any questions?
Sir, what is the reason of finding h of omega? What is the reason for that?
H of omega, actually see, if you solve this in frequency domain, it is easier to solve. In two ways we can solve this. One is y of t, we can find out convolution of x of t and h of t. Okay, convolution of x of t and h of t. Then y of t we can find out. From that maximum value we can find out. But the problem is it is somewhat difficult to find the convolution of x of t and h of t here. Okay, that's why to make the analysis simpler, we will solve this in the frequency domain. That's why we are finding out h of omega and x of omega, mainly h of omega. Actually we can solve this in two ways. As I said, you can find out x of omega, h of omega. So you can find out the product, then what you get is y of omega. Now you can take inverse Fourier transform, so y of t you will get. Or for this is the very standard one for cos or sine or e power j omega kind of thing. That means uh, sinusoids and complex sinusoids, they are, if they are passing through some LTI system or filter, then the shape will be retained as it is, only the magnitude will be scaled by this, and some phase will be added. That's why we are finding out h of omega. Is that okay? You can try later. You try to find out the convolution directly in time domain. It's very difficult to solve actually. That's why we don't do in time domain. This you can do in frequency domain. We can do it. X of omega we can find out. H of omega we can find out. We can multiply. We'll get y of omega. Then inverse Fourier transform you take. Y of t you'll get. But this is also somewhat lengthy. That's why this one will go. Okay. So, but if some LTI system is there, h of omega, suppose if you are giving input some a sine omega naught t some theta, then h of omega, if it is a complex quantity, it will have magnitude and phase. If it's a real one, then there is no phase. At omega naught, you find out magnitude and phase. The output is same signal, but the amplitude is multiplied by the magnitude. H of omega naught into phase will be added. This is very standard one. We will find out this kind of problems in GATE. So that's why I found out h of omega, this one. Now at that frequency, what is the magnitude and phase? Phase is 0. So what is the magnitude? With that magnitude we are multiplying. For 200 pi, the magnitude is 2. So this is multiplied. For the second one at 400 pi, the magnitude is 0 because h of omega is ranging from minus 300 pi to 300 pi. The second term will become 0. Is that okay?
Yes, sir. Yeah.
Yeah. Any other questions? Fine. Let's move to the next question. So read out this question. This question was given in GATE 2015 ECE set 2 for 2 marks. The signal cos 10 pi t plus pi by 4 is ideally sampled at a sampling frequency of 15 Hz. The sampled signal is passed through a filter with impulse response. The impulse response is given. What is the filter output? Can somebody like tell me how we can approach this problem? Based on sampling, one problem we have done in our last class. In the similar way, like whatever problem we have solved earlier, the first problem, the similar concept we can apply. But here the signal is first going through a sampler. So suppose x of t is a signal. This is first is going through a sampler. Okay, with sampling frequency f of fs 15 Hz it is given, 15 Hz or 15 kilohertz. 15 Hz it is given. Okay, now let us say the output of the sampler is x del of t. Now this is passed through a filter h of t. Then what is y of t we need to find out. Okay, the signal x of t and passed through a sampler whose sampling frequency is 15 Hz. Then the sampled signal is passed through a filter whose impulse response is given. Okay, the similar way, so we need to find out this x del of t and h of t is given from this h of y of t is x del of t convolved with h of t. Then we need to find out y of t. Okay, first x of t passed through a sampler with sampling frequency 15 Hz. We'll get x del of t sampled version of the signal. Then it is passed through h of t, some filter. Output of the filter is input convolved with h of t, x del of t convolved with h of t. Y of t we need to find out, but dealing in time domain is somewhat difficult, so we will deal this problem in the frequency domain. Okay, and first to understand this we should know how this x del of t looks like. Okay, if we know x del of t, we can find out its Fourier transform x del of omega, and also we can find out h of t's Fourier transform h of omega. Then in frequency domain somewhat easily we can deal with this problem. Okay, first we'll try to understand the about sampling. In the question it is given the signal is ideally sampled. Can somebody tell me how we can get the sample signal? We know, right, why we use sampling. So instead of sending the entire signal, let us say we have some signals like this x of t. So instead of, let us say we want to transmit the signal, instead of transmitting the signal as it is, we will take the signal, we will sample the signal, take some values, discrete values. We will take discrete values of the signal. Let us say these are the samples, and only these discrete values only can be used for further analysis. Okay, that means instead of the entire signal, we will take the samples of the signal at discrete intervals. Let us say these are the samples. These are the samples. Okay, these samples are spaced at an interval ts. Only the samples only will be like we can use for any other purpose. And also we should select the samples. The spacing between samples should be such that we will be able to reconstruct the signal from the sample signal. That means in the future, suppose this is the sample version of signal, only samples we are taking. Suppose in the future, if we want to reconstruct the original continuous signal, we should be able to reconstruct that from this. It is passed through some filter. We should be able to reconstruct it. Okay, na? For that purpose, the sampling frequency should be this, I guess, twice the greater than or equal to the 2 times of maximum signal frequency. Let us say x of t has maximum signal frequency f of m, then sampling frequency should be more than 2 fm. This is Nyquist criteria. Fs equal to 2 fm. This is Nyquist criteria. If it is less than that, we will not be able to reconstruct back the signal from the sampled version of the signal. Now, how to get the sample signal now? This is what sampling. Sample means how to get the sample signal. The signal is multiplied with some impulse train. So this one impulse train sigma n equal to minus infinity to infinity del of t minus nts. Then we will get the sampled version of the signal. So x of t is this, some signal x of t. Now this is multiplied by the impulse train. Impulse train, see, del of t, where it is have value, non-zero value at the inside brackets, whatever that quantity, when it is 0, it is having non-zero values, right? So for n equal to 0 and n equal to 1, it is a ts, 2ts, like this. So this is the impulse train actually. like this, so on. This is this impulse train. So the see, you can see the spacing between them is Ts. This is called sampling interval. Sampling interval, and frequency omega s is 2 pi by Ts, or Fs is 1 by Ts. Okay, if x of t is multiplied with that, then we will get the sample version of signal. So sample signal is x del of t, we say. Then what we get is, oh, this one is the, sorry, this one is the sampled version of the signal. This is the x del of t. Now we will see what frequencies are there. So what we can do for this problem, x del of t we need to find out, this one x del of t, and h of omega we'll find out. H of omega we will find out, and x del of t we will find out. For this we should see what are the frequencies are there in this. So based on that we can find out the output. Okay, so for that what we will do, we will find out the Fourier transform of x del of t, that is, let us say x del of omega. Now our x del of t is x of t into impulse train sigma n equal to minus infinity to plus infinity del of t minus n ts. Now if you see, I want to find out the Fourier transform for this Fourier transform. So we can see this is one signal, this is another signal. In time domain, product of the signal. So in frequency domain, so in the time domain, let us say we have two signals, x of t and to y of t. In the frequency domain, what is the Fourier transform for them? 1 by 2 pi into, x of omega convolved with y of omega, right? In the same way, to find out the Fourier transform of this, so that is, let us say x del of omega. So this is one signal, treat this as one signal, treat this as another signal. Now we have to uh, that product in the time domain will become convolution in the frequency domain. Let us say Fourier transform of x of t is x of omega convolved with, and Fourier transform of this impulse train, the Fourier transform of impulse train is, I'm writing here. So this we need to find out actually, just directly I'm writing here, sigma n equal to minus infinity to plus infinity del of omega minus n omega s. This is the Fourier transform of the second signal. Okay, so x, let us say our signal is x of t. In the problem it is given, sorry, we have already x of t, we have cosine signal. Now let us say this 2 pi will get cancelled, and by using the convolution property of impulse response, we can write this like x of omega minus n omega s. This is the Fourier transform of the sampled version of the signal. We know last class we have discussed the convolution property of impulse is what? X of t convolved with some del of t minus t naught. Then what we get is x of t minus t naught. In the same way, x of omega is convolved with this, summation is there. So what we get is 1 by ts into sigma n equal to minus infinity to plus infinity x of omega minus n omega s. If we have any confusion in this, we can write this like x of omega convolved with del of omega plus del of omega minus omega s plus del of omega minus 2 omega s, like this. We expand this side also del of omega plus omega s, like this. So convolution, individual convolution we can take. So this is the Fourier transform of the sampled signal. X del of omega is 1 by ts integral minus infinity to plus infinity x of omega minus n omega s. Here omega s is nothing but the sampling of frequency, that is omega s is nothing but 2 pi fs or 2 pi by ts. Okay, now we have like our signal x of t, that is given cos something is given. From that we can find out x del of t or also x del of omega we can find out. Okay, so our signal is given, our signal is cos 10 pi t plus pi by 4. So our x of t is given cos 10 pi t plus pi by 4. For this we need to find out the Fourier transform because x of omega we want, right? So for this Fourier transform we have to find out, it is x of omega. Now we know cos omega naught t, let us say if we have, what is the Fourier transform for this? Pi into del of omega plus omega naught plus del of omega minus omega naught. Two impulses, right? Two impulses at omega naught plus omega naught and minus omega naught. How to find out this also I'll just explain here. So for one we know what is the Fourier transform for one. Just now we discussed it, 2 pi del of omega, right? 2 pi del of omega. Now this cos omega naught, how I will write? Cos I can write e power j omega naught t plus e power minus j omega naught t by 2. Now this is like 1 into e power j omega naught t, right? So it is like now 1 into e power j omega naught t. Now we can use shifting property, right? This is what? 2 pi into del of omega minus omega naught, right? So we know if x of some x of t has Fourier transform x of omega, then x of t into e power some j omega naught t. This Fourier transform, what will happen in the frequency domain? It will be shifted by omega naught. This property I am using. For 1 2 pi del of omega we know. Now into e power j omega naught t, it is shifted. So for this what will happen? 2 pi into first one, this one, del of omega minus omega naught. For the second one, del of omega plus omega naught by 2. This 2 will get cancelled. So we'll get this pi into del of omega plus omega naught, omega minus omega naught. So that is the Fourier transform of cos omega ct. And if you see here, this pi by 4 is just a phase. So this phase I can just express like this, e power j by 4. So since it's a sinusoid signal, the phase separately we can express like this. So just like this I am expressing e power j pi by 4. Now for cos 10 pi t plus pi by 4, what will be the Fourier transform? This phase separately I am expressing. Now for cos 10 pi t, the Fourier transform is del into pi into del of omega plus 10 pi plus omega minus 10 pi, and there is this phase is there. Let the phase be aside, later we'll see about it. Okay, or else you can try it later. You can also do like this. So cos 10 pi t plus pi by 4 I can express like this, cos of 10 pi into t plus 1 by 40. It is like time shift property, right? Using time shift property also you can find out. But anyway, for other signals we can use like this. Since it's a sinusoid signal, the phase separately I can express like this. So for this phase I am expressing separately. So our x of t, its Fourier transform is cos 10 pi t, this one, right? This is the Fourier transform. So we have two impulses at 10 pi and minus 10 pi. This is our x of omega, and it is having some phase e power j pi by 2 phase is there. Okay, this is our x of omega. Now what is our x del of t? Fourier transform of x del of omega is what? The sampled version of the signal, its Fourier transform is 1 by ts. Just now we have seen this one, 1 by ts into sigma n equal to minus infinity to plus infinity x omega minus n omega s. 1 by ts into sigma n equal to minus infinity to plus infinity x of omega minus n omega s. So what is ts? Here fs is given, right? Fs is 15 Hz. So in the problem fs is given 15 Hz. So ts is what? 1 by fs. So sorry, 1 by ts we want. 1 by ts is same as fs, right? So 15 only. And what about omega s? Omega s is 2 pi into fs, right? So 2 pi into 15, 30 pi. So our Fourier transform is of the sampled signal. This is the Fourier transform of the sampled signal x delta. 1 by ts is 15, sigma n equal to minus infinity to plus infinity x of omega minus 30 pi into n. Omega s is 30. So this is the Fourier transform of our sampled signal. So if you see the block diagram here, this is the input x of t. So this is input our x of t, and after passing through sampler we are getting x del of t. Its Fourier transform is x del of omega. This I am finding out. This is what we got here. So this you can also express like this. 15 into n, we can n minus infinity to plus infinity you can give. You can say like so on. When n equal to minus 2, it is omega plus 60 pi. N equal to minus 1, it is omega plus 30 pi. When n equal to 0, it's x of omega plus x of omega minus 30 pi plus x of omega minus 60 pi, so on like this. This is the Fourier transform of the sampled version of our signal. Now in the form of this graph I'll represent. So this is x of omega. We know x of omega is this one. Now this is shifted version, right? So x of omega is what? It is having two impulses at minus 10 pi and plus 10 pi. So if it is 0, this is x del of omega, let us say. It is having two impulses at minus 10 pi and plus 10 pi. This one, right? When n equal to 1, if I give, what will happen? When n equal to 1, this one, right? X of omega minus 30 pi. When n equal to 1 and x of omega minus 35. 30 omega minus 35 means what? X of omega is shifted by 30 pi towards right, right? So it's right shift. You have to shift it by 30 pi. That means what we'll get already, this is x of omega. So this is x of omega. Now we shift it by 30 pi. What you will get? If you shift it, you will get somewhere here at 20 pi and somewhere here at 40 pi you'll get. This only shifted like this. So this is what? X of omega minus 30 pi. Similarly, the left shift, that means x of omega plus 30 pi. X of omega plus 30 pi is left shift. So the same x of omega we have to shift it towards left. So you'll get somewhere here minus 20 pi, two impulses at minus 20 pi and minus 40 pi. This is x of omega plus 30 pi. Like this, after that you have to draw x of omega plus 60 pi and x of omega minus 60 pi. Like that you will get infinite impulses you will get. Okay, we will get infinite impulses, but also we have the extra phase is here and 15 is here. This 15 is the scaling factor. So that extra I am just writing here. So 15 is the scaling factor and extra phase e power j pi by 4. This is there already. This one e power j pi by 4 extra phase is there, and 15 is this amplitude. So this is the signal Fourier transform if you draw on the omega domain. Okay. Now what we have to do, we have to find out h of omega. We have to find out. If we find out h of omega, then we can see what will go to the output. Now what is h of t? H of t is what? Sine pi t by pi t, sine pi t by pi t into cos 40 pi by t minus pi by 2. Now we have to find out h of omega. We need to find out. For this, how we can find out Fourier transform? I can write this as sine pi t by pi t into e power, this phase I am separating out like earlier, e power minus j pi by 2. This is the phase. Separately I am writing. So this the phase I am just writing here, separating out to make it simpler. So e power j 40 pi t plus e power minus j 40 pi t by 2, right? So cos we can write like e power j theta plus e power minus j theta by 2. Now we know how to find out the Fourier transform for this. Let us say if this one is g of t, then the g of t is multiplied by what? Something like e power j omega naught t plus e power minus j omega naught t, right? So frequency shift will be there. This kind of thing already we have seen. Now sine pi t by pi t, what is the Fourier transform for this? We have seen. For this the Fourier transform is from minus pi to plus pi. You will have a rectangular pulse g of omega. If I say g of t, this is g of omega. Okay. Now this will be shifted towards left and right by 40 pi because it is multiplied by e power j 40 pi t and e power minus j 40 pi t, right? So this I'm writing, see, e power minus j pi by 2, that is the phase. This 2 extra 2 I'm writing here into g of t. Our g of t is sine pi t by pi t into e power j 40 pi t plus e power minus j 40 pi t. Now what will happen? This is shifted both sides, right, by an amount of 40 pi t. So if I draw this h of omega, so this anyway this phase and this magnitude will be there. Now this is shifted by an amount of 40 pi. Here 40 pi minus 39 pi plus 39 pi. Okay. Similarly, this also shifted towards left because we are multiply with e power j 40 pi t right shift and e power minus j 40 pi t left shift. So minus 40 pi minus 39 pi minus 41 pi. So this is our h of omega, e power minus j pi by 2. This is the phase and 1 by 2 scaling factor. This is our h of omega. Okay. Now we have our h of omega and we have our x del of omega. Then we will know what frequencies will go out of it. So y of t or y of omega we can find out, right? So if you see, we have our x del of omega here. Now you tell me what frequencies will go to the output of the filter and what frequency will be stopped by the filter. So okay, x del of t is here. So I'll write, I'll draw that h of omega, just I'll draw here. This is our h of omega. This is our h of omega. You have like a band pass filter 40 pi, 41 pi minus 39 pi. Similarly here minus 40 pi, 39 pi minus 41 pi, and we have this phase e power minus j by 2, 2. Okay, this is h of omega. Now you tell me we have x del of t and h of omega. Now what frequencies will go out of the filter and what frequencies will be suppressed? Can somebody tell me? Now if you see here, the pass band is from 39 pi to 41 pi, right? So if you see here, only this will go because the pass band is 40 pi. So only this impulse will go 40 pi and 40 pi. These two impulses will be allowed by this filter where the gain is non-zero, and the other one, the all other will be uh, suppressed because there the gain is 0, right? Only those impulses will go out of the filter. So we can get y of omega, we can get something like this. Only those only will go out of the filter. This 40 pi t, one impulse is there, and minus 40 pi another impulse is there, and remaining all will be suppressed. And also this phase and magnitudes we have to multiply. Here 15 into e power j pi by 4, and here 1 by 2 into e power minus j pi by 2. Okay, this is y of omega. That means now if I take inverse Fourier transform for this, you have two impulses at minus 40 pi and plus 40 pi. It is cos, right? It is nothing but cos. So it's if I take inverse Fourier transform for this, its inverse Fourier transform is what? Cos of 40 pi t, right? Two impulses at these two. And here we have 15 by 2, the scaling factor is 15 by 2, and extra phase is there, e power j pi by 4, e power j pi by 4 into e power minus j pi by 2 into cos 40 pi t. So this phase becomes, total phase becomes e power minus j pi by 2. So this entire signal I can write like 15 by 2 into cos 40 pi t, the phase will go inside minus pi by 4. So this is pi by 4. So 15 by 2 cos 40 pi t minus pi by 4. If you see the options, the first option is that one. 15 by 2 cos 40 pi t minus pi by 4. Now have you understood? Please feel free to ask if you have any questions. Okay, the overall procedure, let me repeat. So this is the filter h of t, and we need to find out h of omega. This one is the filter, and input to this is the sample signal. Okay, and output we'll get something y of t or y of omega, frequency domain y of t, y of omega, time domain y of t. So for this we found out the Fourier transform h of omega we found out. So we got something like this. It's Fourier transform. But in the problem only x of t is given, x del of t is not given. Sampled version of the signal is not given. So x of t we have. So from that we found out x del of t. Okay. For the x del of t, we also found out the Fourier transform x del of omega. So what we got x del of omega? Something like this. Many impulses we got. Right, infinite impulses we got at 10 pi, 20 pi, 40 pi, like that, right? Now when this x del of t is passed through this filter, what will happen? Where the filter is having non-zero gain, those impulses will reach out of the filter, the other impulses will be suppressed. This we have seen the pass band for this filter, what we got 39 pi to 41 pi, also minus 39 pi to minus 39 pi to minus 41 pi we got. That means only the impulse at 40 pi and minus 40 pi will reach out of the filter, and all other will be rejected because there the gain is 0. Okay, so that's what you can see here. Like this, many impulses will get in x of omega, x del of omega. All other will be suppressed except these two impulses at minus 40 pi and plus 45, because they will fall here at this region. All other will fall where the gain is 0. So all other will be rejected. Only these two impulses we will have at the output. Okay, this magnitude and phases we are taking as this. Okay, na? This phase and magnitude. If you take inverse Fourier for transform for this, so it is cos 40 pi t, because omega is here, omega c is 40 pi. So 15 by 2 is the magnitude. Phase is e power j pi by 4 into e power minus j pi by 2. So phase minus pi by 4 will get. Okay. Any doubts? Fine. We have no doubts. We can stop here. And actually, only we could solve two problems today. In our next class, we will solve some problems from Fourier series, that is continuous Fourier series. Okay, few problems from Fourier series, and also some problems from digital electronics, maybe one or two problems. If time permits, one or two problems we will solve from control systems. Okay, mainly we'll solve from Fourier series, then digital electronics, signals and digital in the next class. Okay, those who have any doubts, you can stay back, or if you don't have doubts, you can join the other session. Thank you everyone. We will stop here.